Okay, first of all, question number 2. Considering the following corollary, for n a positive integer, the largest of the binomial coefficients of the sequence, this is the sequence of binomial coefficients, we want to prove the largest of binomial coefficient n, the floor of n divided by 2 is the same as the n of the ceiling of n divided by 2. Okay, now we want to prove the corollary. First of all, we must know the theorem of 5.2.1, which is the sequence of binomial coefficients is a unimodal sequence. Okay, what it means is when n is even, the n up here is even, so the sequence will increase up until a point where it will decrease again. Okay, for even. Okay, for odd, however, it will increase until one point, the n minus 1 divided by 2, and the next term of n plus 1 divided by 2 will be having the same answer. Okay, then it will decrease again. Okay, that is the theorem of 5.2.1. Okay, now let's consider the change of the unimodal sequence of binomial coefficients. There are 3 situations. First is where the initial term and the next term, the initial term is smaller than the next term, meaning it's increasing. Okay, the second situation is when n of k minus 1, which is the initial term, is equal to the next term, which happened right in the middle here. And for the even is the same term, while for odd it's the initial term and the next term, they are the same. Okay, so for the third situation, the initial term is bigger than the next term, so it's decreasing for both even and odd n. Okay, now, okay, continuing for just now, let's consider the change of unimodal sequence of binomial coefficients, and there are 3 situations. So what we want to do is we want to see the relationship between the initial term and the next term. Okay, so what we do, we use the quotient to find their relationship. Okay, first of all, for the combination of n to k, the binomial coefficient, it's n factorial divided by k factorial times with n minus k factorial, and the n k minus 1, n c k minus 1 is n factorial divided by k minus 1 factorial, and n minus k plus 1 factorial. Okay, to make it simpler, we have to times k minus 1 here and k minus 1 down below. After we times with k minus 1, we can cancel out this one and this one. So the thing remain will be k when times with k minus 1 factorial. The thing left will be k. So k is left down here, and down here left n minus k plus 1 factorial. Okay, so now it becomes like this. Now I want to make it simpler again, so I times with n minus k factorial above and below. Okay, now I can see there's n minus k factorial up here, so I can cancel it out. What left is n factorial divided by k divided by n factorial divided by n minus k plus 1, which is the what's left when you divide this n minus k factorial by n minus k plus 1 factorial. This is what left, n minus k plus 1. So now I want to make it simpler again, so I separate it. So n factorial divided by k, this is actually divide, but when we divide something, we need to terbalikkan the fraction behind. So I change the denominator and the numerator straight away and write it down. Okay, right at this step, we can see there's n factorial up here and n factorial down here, so we can cancel it out. what left is when n minus k plus 1 over k. This is the relationship between n of k divided by n of k minus 1. Okay, using the relationship that we find just now between n of k and n of k minus 1, we can proceed here. Okay, proceed down here, the one that we considered just now. When n, let me put it side by side. Okay, when n of k minus 1 is smaller than n of k, then we can see above here is n of k, so the n of k is n minus k plus 1. N minus k plus 1. And the n of k minus 1 is actually, n of k minus 1 is down here, so down here is k. So k is less than n minus k plus 1. This one, we got it from the relationship we used just now, the one that we used quotient to find. Okay, the next one is just the same. So n of k minus 1 is k equal n of k, it's n minus k plus 1. Okay, this is just the same also. K is bigger than n minus k plus 1. Okay, now we get 3 different inequalities again. Okay, let's consider the situation just now. Okay, there's 3 Ks, the one that we get just now. So let me label this one as A, the small a. Let me label this one as small b, and this one as small c. The small a is k less than n minus k plus 1. Okay, let me move to another page. So, from A, which is k less than n minus k plus 1, we solve the linear inequalities. We'll get k less than n plus 1 over 2. So, for this case, we need to consider whether we need to consider when n is even and when n is odd. First, let's consider n is even. Okay, when n is even, the n plus 1 over here was supposed to be a whole number. Okay, so when it is a whole number, the n plus 1 must be a whole number, must be an even number. So let us just put it as n. Okay, so k is less than or equal to n over 2. Okay, this is for when n is even and when k is less than n plus 1 over 2. So what if when n is odd? Okay, when n is odd, we can look from the theorem 5.2.1. Okay, put it here. Theorem of 5.2.1 says that when n is odd, the k that is less than n plus 1 over 2, less than this one, will be less than or equal to n of n minus 1 over 2. Okay, so you can see it here. I wrote it down here. K is less than n plus 1 over 2, or k is less than or equal to n minus 1 over 2. This is from theory 5.2.1. Okay, this is only for the first situation where k is smaller than n plus 1 over 2. So what if from B? From B just now, the B is k equal to n minus k plus 1. What if when it's the same or when it's constant? Okay, so 2k, we can solve this equation. 2k is actually equal to n plus 1. Now we consider the case of when n is even. Okay, when n is even, we can see that 2k cannot be n plus 1, because if n plus 1, it will be odd. So what this implies is that for n is even, for the sequence of binomial coefficient with n even, there is no two consecutive terms that are equal. which means all the terms sitting next to each other are different. Okay, consider the case of n. Consider the case when n is odd. Okay, so when n is odd, the 2k can be equal to n plus 1. So the k will be n plus 1 over 2. This means there is two consecutive terms that are equal. Okay, however, from this case, actually we can see from theorem 5.2.1, write down here, theorem 5.2.1. okay, we can actually see that when the terms that are equal are actually these two, the n of n minus 1 over 2 and the n of n plus 1 over 2. These two terms are the equal one. I write it down here. n minus 1 over 2 is actually equal to n plus 1 over 2. These two are the equal term. Okay, this is what this means. Okay, from C, we can see from C, k is bigger than n minus k plus 1. So the k is bigger than n plus 1 over 2. Okay, for this one, if n is even, then k is bigger or equal to n over 2. This is just the same as the part A just now. When I say n plus 1 was supposed to be, n plus 1 over 2 was supposed to be a whole number, so we can just rewrite n plus 1 as n. So the same one, I rewrite it as n. So k is bigger than or equal to n over 2. Okay, now what if the case where n is odd? Then we can see from theorem 5.2.1. Okay, k is actually more than n minus 1 over 2, or k is bigger than or equal to n plus 1 over 2. Let me show you the theorem. Okay, k is less than n minus 1 over 2. K is less than n minus 1. When it's less than n minus 1 over 2, because this is bigger, the binomial sequence is decreasing right here. So this k is bigger than this one, or k is bigger or equal to than this one. Okay, so this is the case when n is odd for case C, where k is bigger than n minus k plus 1. Okay, now let's look at the idea of floor and ceiling. The floor of x is the greatest integer less than or equal to x. The ceiling of x is the greatest integer bigger or equal to x. When n is even, okay, the floor of n divided by 2, or n over 2, is equal to the ceiling of n over 2, which is equal to n over 2. The reason I say so is, when n is even, it divides by 2 will become a whole number. Okay, so a whole number, the floor and the ceiling of a whole number will be the whole number itself. So that is why I say the floor and the ceiling of n over 2 is just n over 2. This is when n is even. What if when n is odd? What will the ceiling and the floor of n over 2 be? For floor of n over 2, it will be equal to n minus 1 over 2. Why do I say so? Let's look at from A just now. If n is odd, then from theorem 5.2.1, the k here will be smaller than or equal to n minus 1 over 2. This is actually the idea of floor that we want to use. K is smaller than n minus 1 over 2. So k, some integer k, is smaller or equal to n minus 1 over 2. So we know that the floor of n over 2 is actually equal to n minus 1 over 2. This is the one we get from here. Let me put like 1. Okay, So we can say this is from 1. Okay, so what about the ceiling of n over 2? The ceiling of n over 2 is actually equal to n plus 1 over 2. And we can get it from C just now. If n is odd, then from theorem 5.2.1, we can see that whatever it is, okay, k is bigger than or equal to n plus 1 over 2. This is the concept of ceiling that we want to use. Okay, k is bigger than or equal to n plus 1 over 2. Let's look at the definition again. So the ceiling of x or of n over 2 is greatest integer that is bigger than or equal to n plus 1 over 2. So which is why I write the ceiling of n over 2 is equal to n plus 1 over 2. This is actually from number 2 here. So go back to this one. This is actually from number 2. Okay, so therefore, what can we conclude? We can conclude that for n, for the n when it's positive integer, the largest of the binomial coefficient is actually when the n of the floor number 2 is actually equal to the n of the ceiling of n over 2. Okay, this is true for n is even, since the floor and the ceiling of when n is even, they are equal to n over 2. So this is they equal to each other, since the floor and the ceiling are just the same. Okay. What if it's odd? When it's odd, the floor will be n minus 1 over 2. Okay. When it's odd, let me write it down. This is when it's even. If n is even, this is correct. What if n is odd? Then the floor of n over 2 will be n minus 1 over 2. So I write n minus 1 over 2. Will it be equal to the ceiling? Okay, let me write it here. N of the floor of n over 2 is actually equal to this one. Okay, what about the ceiling of n over 2? What will it be equal? It will be equal to n. The ceiling is from here, we can see n plus 1 over 2. So n plus 1 over 2. Will this be equal? Okay, this is why we proved just now. Okay, where do we stop just now? So therefore, we can conclude that when n is even, the n of the floor of n over 2 is equal to the n of the ceiling of n over 2. Okay, what if when it's odd? When it's odd, the n of the floor of n over 2 is actually equal to the n of n minus 1 over 2. Where do I get this one? It's actually from here. The floor of n over 2 when it's odd is equal to n minus 1 over 2. So I can write the floor is actually equal to n over 1 over 2. N minus 1 over 2. What with the right hand side, the left hand side? The left hand side, the n of ceiling of n over 2. What is it equal to? Is equal to n of n plus 1 over 2, which I get from here when n is odd. Okay, so now the question is whether these two, they are equal. If they are equal, then this is proven right for both even and odd case. So now let's see whether it's equal. Okay, this one, if is the right hand side, n of n minus 1 over 2 is the right hand side, and left hand side is n plus 1 over 2. Where can we prove this? We can actually prove this equal from theorem 5.2.1. Okay, let's look at theorem of 5.2.1. Okay, from the theorem of 5.2.1, we can see that the n of n minus 1 over 2 is actually equal to the n of n plus 1 over 2. So, write it out here. The n of n minus 1 over 2 is actually equal to the n of n plus 1 over 2. You must realize that this is actually the right hand side that we do just now, and this is the left hand side that we do just now. Okay, so the right hand side is actually n of the floor of n over 2. So n of floor of n over 2 is equal to the right hand side, which is n of the ceiling of n over 2. So n of the ceiling of n over 2. Okay, now that we have proven the right hand side and the left hand side are the same from the theorem 5.2.1, we can say that this equation, that is n over n, this corollary, which is n over 2, the the floor of n over 2 is just the same as the n of the ceiling of n over 2. This is true because we have proven it true for even case and for odd case. That's all. Thank you. And if you have any hesitation, you can call me to ask me, or you can ask me on WhatsApp. You can ask me in the class. You can ask me anywhere. Thank you very much.